So like I was saying today, aka Monday, we can't really measure a reaction rate directly for monitoring an experiment, but we can monitor concentrations over time. And therefore, it's often very helpful to study the integrated rate law, which tells us how concentrations should change over time. How concentrations change. So suppose we have a reaction, let's say A plus B goes to C. So we don't know what the rate law of this reaction is a priori, but we can maybe predict some things if we were to, let's say, assume that it is first order, second order, zero order, et cetera, et cetera. So as one example, suppose that it's first order. First order in A, then we'll know that our rate must be K. And so if we're saying first order in A, zero order in B, then it's overall a first order reaction. So just ignore the B. So it's first order in A. So if we want to figure out what the integrated rate law is, we'll first start off with the actual rate law. So by this equation, what we mean is that the consumption of A over time equals Ka. And then so if we integrate this, we'll move dt to the other side, A to this side, and then we'll integrate from, let's say, A at times t to our A0, our initial concentration of A. And then so this will be 1 over A dA. And then so this equals negative, and then we're integrating from time t to time 0, K dt. And then if we then integrate, let's see, so if we solve this integral, which I'm sure all of you are better at doing this than I am, then we have log A at time t minus natural log A at time 0 is equal to negative kt. And there, finally, we get to move our logs around. Negative kt. And therefore, A at time t equals our initial concentration of A, e to the negative kt. So this is our integrated rate law for a first order reaction. So we know how the concentration of A should change over time. It should be related to e to the negative kt. And so this is our integrated rate law. And therefore, if we're running our experiment, here's t, and we're measuring the concentration of A over time, we expect to see something like that it'll decay over time, as we expect for a reagent. And so this point over here is our initial concentration. And then we could fit this. Alternatively, you might have seen linearization methods. So if you want to kind of if you want to assume that it's first order, and then you could try to fit this data to this equation, and if it fits very well, then that supports your little proposal that it is first order. Alternatively, we could also try to plot t versus the natural log of the concentration of A. And then if we see that, like, so if we plot this log, then you can see that if we plot the log, it's going to be actually linear versus time, so negative kt. So therefore, we should expect to see a line. And then, so this slope equals negative k. And then also, this intercept at time 0 is then going to be, well, it's actually going to be the natural log. Natural log of A0, or A0. So there are kind of two ways to process the data for a first order reaction. OK, what did I want to say? Oh, and let's see. as a natural consequence of this integrated rate law, we could also talk about the half-life. Half-life, which is also shown as T1/2. And so the half-life is the time at when A equals 1/2 of our initial concentration. So that's the time that this happens. And so we could solve for this using our integrated rate law. So let's see. Doop. So if again we take our log of, in this case it'll be A0/2. So this is at the time when our initial concentration is halved. This equals negative K T1/2. And therefore equals, so let's see, this crosses out, this negative moves to the other side, so this will be natural log 2 over K. Remember, negative log is going to be 1 over this, so that's why the 1/2 turns into a 2. So as a result, what you can see, this is our half-life for our first order reaction. And then, let's see, what's key about this is concentration independent. So for any first order reaction, it doesn't matter how much you start with, it only matters the rate constant, K, that determines how long the half-life is. And so this is typical for radioactive decay, for example, which is typically first order. So by knowing I guess, how much you have left, you can kind of translate to the half-life, and then you can find your rate of decay. So that's the first order reaction, the integrated rate law. All right, let's move on to other orders of reactions. Let me quickly erase. Oh yes, and apologies, the outline, I put the half-life kind of at the end, so you have to kind of skip back and forth. But I'm sure you can handle it. Okay, so back to this problem of A to C. Suppose that we're second order in one component. Second order. And then, so in this case, let's suppose we're second order in A. So again, our rate of consumption of A is going to be equal to, again, the rate constant, and then this time to the concentration of A squared. I will point out, so I could have a second order reaction where it's first order in A and first order in B. That's a little bit more complicated to integrate. We'll get to that maybe next week. So after the exam. Okay, so for this second order reaction, we can again solve our differential equation. So move everything to one side. A over A squared equals negative K dt. So again, we integrate, and I won't go through it, but suffice it to say our final integrated rate thing is 1 over A t at time t minus the initial concentration of 1 over the initial concentration of A equals negative KT. Oh wait, no, it's just KT. And then, so therefore, our concentration of A times T equals 1 over plus KT. Sorry, I missed a negative there, but this is correct. And then, so this is how our concentrations behave over time. And then if we again try to plot our concentration of A versus time t, so initially we're still going to get some sort of decay. it won't be exponential decay. So if we try to fit it to exponential decay, it's not going to work. Alternatively, you could also plot the reciprocal. So what we could do is plot T versus 1 over the concentration of A. And then what we'll see is some sort of line. And then our intercept, of course, will be A at time 0. And then, or no, it's 1 over A times 0. And then this slope, again, will be K. Sorry, I got a little confused. So this is our linearized equation. This is the integrated rate law. Integrated rate law. But if we linearize, if you take the reciprocal, so this is linearized, right? So here, 1 over A times T equals KT, so this is the slope. And then the intercept will be 1 over A at time 0. So, OK. So second order reactions. Let's see. Oh, and lastly, I'll let you solve this on your own, but the half-life of a second order reaction is going to be equal to 1 over. So in this case, the half-life is dependent on the initial concentration. So this is concentration dependent, unlike that first order reaction. OK. Let's see. So, and I'll just do one more. Obviously, this is not comprehensive. There are other types of reactions out there that are more complicated, but this is just the general gist of how you begin to solve these. We'll do some more complicated problems in class and maybe in the next week as well. OK, so 0 order, lastly. 0 order. So in this case, what we're going to say is the rate of consumption of A is concentration independent entirely. So this will just be K. So obviously, what we can then do is integrate. So we'll integrate dA. This equals negative K dt, which will integrate from T to 0. And then, let's see. So what this should give us, if I'm doing my math right, hold on. Boop, 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 boop. Ah, yes. So this should give us A at times T equals times 0 minus KT. So this is basically just going to be a straight line down. Boop. Time A. And unlike the other first order, second order, it doesn't kind of decay like that. It just decays down linearly. So this would be the hallmark of a 0 order reaction. OK. And let's see. If you want to solve for T1/2, so let's see. OK. Let me quickly do this. 0 over 2, therefore, equals so T1/2 over 2K. Ta-da! OK, so here's our half-life. Half-life. Here is our integrated rate law. Integrated rate law. OK, so it's pretty straightforward. I'm doing 0 order, first order, and second order, even though we can have maybe multiple components, because in the next week we'll talk about how we can maybe separate off the contributions of multiple reactants, and then we can isolate 0 order, first order, second order, and that's one way to derive a more complicated rate law. So we'll get to that next class, or next week. So this coming class we'll do some practice problems doing these simple variants, and then we'll move on to more complex examples. OK, bye-bye.